Okay, so life on the hard stuff. Curable addiction. Solvable problems. So this is a life lesson. So all academics have a PhD. It's a doctor in philosophy, regardless of what subject you do. So basically, we all like to fancy ourselves as philosophers. This might descend into amateur philosophy, then if that's right with you. So why did I pick this title? Well, academia is difficult, and academia is inherently difficult. And how many of you are interested in research as opposed to industrial practice? Yeah, so 2 or 3, 4, 4.5, 5.5. Yeah, and the rest of you somewhere in between industry, definitely. Yeah, something like that. So there's no right and wrong answer to this. So it's slightly irritating because I hear criticism I shouldn't. So I've made all the mistakes, and yet I have a very, very fulfilled life as a result of having made all these mistakes. So you've heard all the things, look for the red flags. I've trampled through all of those red flags. I've made all of those mistakes, and I'm still here. And I quite like it that way because I get to do what I like. I can do whatever I want. Is this recording? I shouldn't say that. It's but it's a pleasure. Academia is a very interesting place to be. It's as interesting as you want to make it, and that's my take on why I'm here. Is that it gives me the freedom to do what I want to do, and unfortunately for me, what I'm interested in are generally things that you can't actually solve. And you would think, well, that makes a rather futile career. Why on earth would you do that? But actually, the unsolvable problems are those that I find most interesting, and I think are generally accepted as being some of the most interesting problems around. Now, my field is not electrical engineering, but I think I teach some of you, I don't know how many of you are in my second year thermodynamics class. So my background is very, very different to most of yours, I imagine. And yet, what you'll find is that I'm probably interested in pretty much the same types of problems as you are. I just look at them in a slightly different way. And so we'll touch on things which have a huge influence on the way that we do computing, for example, and how we handle distributed systems. So that's something that interests me. Now, you've heard a little bit about that already, but the scale at which I need to work in order to solve my problems in my field you need to tackle them in a slightly different way. And so I'll touch on these things, but I thought for a talk like this, much better and possibly more interesting for you and more interesting for me, if I'm honest about it. You know, I'm really only doing this for my entertainment. But I like eye candy, and the main reason that I'm in the field that I'm in, which isn't thermodynamics, which is what I teach some of your cohort. But my field is the mechanics of fluids, so I'm interested in how fluids move and continue work, and so it's one of these disciplines that falls sort of in between the cracks somewhere. And that's why I end up having to know a reasonable amount of amateur computer science and a reasonable amount of amateur mathematics and a reasonable amount of amateur mechanical engineering. I'm an expert in none of those, and so my background is in aerospace engineering, and I would say I know very little about that as well. But such is the humility that comes from working for a long time on difficult problems. Oh, is it? It's not sharing properly. So is it manual switching? Oh gosh. There we go. Right. So so this is life. In the absence of fluids. Is there a third party in control of it?
I stand here, so.
You won't need it for much longer, but actually it will help. Basically, I've got a whole pile of eye candy here, and we'll see how much we get through. Variety of static images, pictures, but it's really just a little walk through my career so far. I started off life as an undergraduate, as I've said, in aerospace engineering. So this was the sort of problem that they gave me to do for a research project. Go and put some cells on a body, and then you build a mesh around that, and then you compute some flow here. So in the top image there, you see mesh, bottom image, you see the answer that comes out of a black box. You press a button and you get an answer. It's the most dissatisfying project I've ever done, and I did it one summer. I got a scholarship to do this, and I decided never again would I want to do something like that. Never say that, by the way. Never say never again, because it turns out that I've spent most of my life. In fact, I've just got a PhD student who's just finished, and the only thing that's different about the meshing that he's been doing is that it's in 4 dimensions instead of 3. So it's slightly different questions he's answering, but that's you know, so nothing changes. I started life doing meshing, and if you work in fluid mechanics, doing any sort of computational work at all, then you spend most of your time fiddling around with where points go in a grid. Most dissatisfying, and so I was very keen to get out of this. And so I ended up going to work for a company you may have heard of called Rolls-Royce. They don't just make cars. In fact, that's a completely separate company now. But they make aircraft engines. And so when I was there, I don't actually have that many photographs or images from that time in my life, because video was something that would be very difficult to produce. The tools just weren't as well developed as they are now, and a lot of it's redacted. So some of the stuff that I worked on is I don't have access to that. But here are a couple of things that I did. This is essentially the before the if you ever travel in a Dreamliner, Boeing Dreamliner. They're all powered by the engine that I used to work on, and one of the features of that engine is these little serrations on the back of the nozzle. And so that was my life for getting on for 12 months. I spent looking at serrations and nozzles, developing technology to be able to optimize. So basically, my job was to take what has historically been a manual process of design and turn it into an automatic computer design. No artificial intelligence required for this. I don't know if you're familiar with the methods involved, but they range from very simple to very complex. So, have you ever heard of gradient descent? Yeah, you have? Yeah. So sophisticated versions of that were what we used to use routinely. Genetic algorithms. Is that a terminology that you've heard of? No? Some of you yes, some of you no? No? No.
We don't teach them anymore.
Don't teach them anymore. Well, that's what we used to use, and they work a lot better than everything else that we had in the toolbox, turns out, at the time. And so using that, I ended up developing this shape, which is used not for jet airliners, but where you've got a gas turbine, and typically they're on things like oil rigs and so on. You get a very dense, high energy power source, but you're space constrained, so you use a jet engine to do that, but you don't want the oil rig to float away. So you need to turn the jet upwards so that it doesn't provide thrust, and so that's some of the stuff that I worked on there. And I liked it. I really enjoyed working in this industry. It's a very invigorating environment, very interesting environment. And immediately I was there, I felt part of a culture. And I'd never felt that before as an undergraduate at all. But I had a very strong feeling that everybody was on the same side, that everybody was motivated by the same goal. And the goal was to keep the company afloat. And if you've heard the news recently, you'll realize that's an open question at the moment. Is Rolls-Royce actually able to keep afloat? So periodically, industry goes through these crises, and it doesn't, I think, matter really what industry you're actually involved with. All industries have cycles depending on where technology has got to, how sales have gone, what economic conditions are. And obviously the pandemic hasn't done them much good because nobody was flying, and they make a lot of their money not from actually selling these things, but from servicing them. So you typically buy them for about 50p and then have a service contract, a bit like your mobile phone. Same concept. Sell them cheap and charge you for the maintenance. And if you're not flying, they don't need much maintenance. And of course, that's what happened over the pandemic. The same thing happened in 1977. So Rolls-Royce in 1977 went bankrupt. And I would say I was there in 2004, and almost 30 years on from that experience that they had, the culture was still, we need to make sure that we don't fall apart. We're liable to fall apart, and we need to keep going. And so that was a very powerful motivator, that everybody was on the same side and everybody was focused on the same goal, keeping the company afloat. Nowhere else I've worked ever since has been like that. Everywhere else, people pull in all sorts of different directions. Everybody's got different motivations. Everybody's got different directions of travel. And so there isn't that sense of cohesion that we got. But eventually moved. I was looking to do a PhD, and they offered me one, but it was a very how can I put it? It was a very uninspiring interview. I won't, because it's being recorded, I won't tell you which university I went to. But I went to. I won't tell you which university I went to, but the interviewer had been essentially strong-armed into taking me on, and this is never something that you want to experience. Because Rolls-Royce wanted to fund my PhD. This is one way that funding can come to PhDs. Companies can say, we want this done, and we've got an employee who would like to do a PhD, so we can send them off to a university, be supervised academically, and work very closely with the company. And if that works, it's a good way of doing it. But my experience, I was sat down, and I was very naive. I was probably 20 or 21 at that stage. I was sat down, and the chap said, well, Okay. And he was very slimy. He was very slimy. Maybe you can start to guess which university this might have been. I said, yes, yeah. Well, come to name the institution. So what is going to minds? Sorry? Go on.
But we got on record.
Oh. No. No. No, this is a major metropolitan university. And so it really was expecting, I really didn't like that at all. And so I sort of, I had to sort of retreat in a way. I was in a very difficult position because, it'd been really difficult to piece together the funding to get everything to work together. And then suddenly, it was just about to mesh. And then I just went, oh, no, I can't do this. But I had other options, and those other options came to fruition. And so in the end, I went to a place called where we did some of this stuff that's here, in fact, and this is sort of working with high-speed aerodynamic flows. Interestingly, this forms the basis. So there's nothing particularly interesting about this problem. It's just essentially what happens when you blow air at a surface at high pressure. And so the application for this is spraying paint. It turns out that there's lots of interesting physics that nobody understands, and so you get ripples in the paint, and you get splodgy paintwork as a result. And people have worked for decades to try and understand what's going on, and they don't know, and I don't know either. But we did some work on it, and that's that. But it started to. This was pre-PhD, so I hadn't actually found any funding at this stage, but I've gone and done this internship. And interestingly, I now effectively teach how to do this in my fourth year course here. So about half of that course is devoted to simulation work of fluids that's very, very similar to this. So you eventually if you study mechanical or aerospace engineering, you have the option to do this sort of thing and learn how to do that and how to generate these images and understand those flows. So that's where I went, and then I went to a different part of this was interesting. Hopefully this video will play. But I started doing experiments, and I've never done experiments before. I was interested in computers, computer simulation, and that's what I did at Rolls, and I'm used to that. And then I started doing things like this, which are just fascinating bits of eye candy. But this is just two fluids. And they mix together, but they're visualized in a slightly misleading way, so that you can see how the structure behaves. So what you have above is basically salty water. Okay, there's nothing, it's just like the sea. And then underneath it, you've got water with a density which is slightly less, so it's slightly fresher. It's got some salt in it. There's also some dye in there, and that's what you're seeing. And then you just watch what happens when you pull out a barrier. And obviously the heavy stuff wants to fall down and the light stuff wants to go up. And they intermingle in this peculiar and beguiling way. And I thought this was fascinating. I'd played with tanks of water. I'd spent endless hours in my bath as a kid. I used to spend all my summer holidays going from stream to stream, damming them up and doing all sorts of things like that. And guess what? That's what I do as a job. So, if you're interested in something, my misplaced advice would be ignore all the red flags and just do what you want, because you'll be much, much happier as a result. In my view, be very wrong. But that's certainly what I've done. So this sort of thing is a study in itself. This is probably one of the greatest mysteries in physics. How this process works, what's actually going on. There's just so much that is poorly understood or not understood at all about what you're seeing in this video. And I'm not claiming that I've solved all of these things, but I find it absolutely fascinating what's actually happening here. And slowly, little by little, we make progress on this. One of the other things I did was play around with chemicals. So if you put some nasty chemicals, nitric acid, and something. Anything smoking here? No, nobody. Oh, you're far too good. So one of the chemicals in cigarette smoke, in fact, one of the ones that will kill you, is what gives you this lovely colour here. So if you ever look at cigarette smoke in sunlight, it always looks slightly blue, and it's a sort of cyany blue because of a chemical called acridine. The clue is in the name, acrid. You don't want to breathe this in. Some people do that, but it's but this acridine allows. It has a very special property which acts like a pH indicator. So you change the. Anybody done? You'll have done physics at school, yeah? Chemistry, maybe. Yeah. So if you do chemistry, you play around with pH indicators, and this is very useful because the way this pH indicator works is basically a quantum process. Because the fluorescence is a process by which electrons move energy levels. Then what you're actually viewing here is a contour of how mixed something is with respect to something else. So it's a very useful way of visualizing things. And so it produces these very pretty pictures, and we took lots of videos, and I spent an entire PhD doing that. So that was 5.5 years-ish doing stuff like that. It was great fun. I also did this as well. So this is work that I did during the PhD, which is generating numerical simulations of my own. So this is my own code. It's called the mobile, and I actually use this for teaching. So this here comes from the sorts of things that I use these days to teach people. I'll show you a few images at the end, maybe to whet your appetite, make you wish you'd taken a subject like mechanical engineering or aerospace. But I'm sure that will have no effect on you. But this gives you some idea of what you can see. So this is a slightly better view of the same kind of process that you saw in the experimental video. A few differences. This is a two-dimensional flow, and what this is doing is effectively extracting statistics. So this is like height, and this is density. So there's a very dense field at the bottom, and it's smoothly stratified. So there's a little grey in there, and then there's a zone of mixing in the middle. And what you're looking at there is effectively the destruction of information. Have you done any information theory? Like that? Yeah. Yeah, of course. Yeah. So what you're looking at here is the generation of entropy, and essentially moving information around in such a way that you lose track of it. And what you end up with is a large amorphous blob of mixed stuff. And so you've lost potency, you've lost availability. And so by doing some experiments and some simulations on this, we were able to identify some quite fundamental things about how entropy behaves. And entropy is a big philosophical topic, which I don't have time and the will to go into today. But this gives you some idea of the sorts of pieces of thinking that come up. One of the other things I did was do some amateur mathematics, and so we actually discovered a new class of differential equation, didn't know exist. I won't go into the details, but that's the answer on the left there. So as you can see, this is completely contrary to all the advice you've just received. You know, do one thing, do it really well, focus on one thing, you'll never go wrong. And it's absolutely true, you'll never go wrong. But I don't have that kind of mind at all. I get far too interested in too many different things to focus on any one of them for too long. So, already in this, there's a lot of stuff. I then had a holiday in France, as you do, for 2 years. Didn't do much. About the only things I did do, I produced that video, which is of a jet in a background mutation. So think of this like a tornado. This is basically the mechanism by which you get tornadoes forming. And what you see in this video is that you start off with a jet, and then you end up with a very broken flow. And then you get it to reform again, then it comes back again. And then it breaks again, and then it'll come back again. And so you get this sort of instability. And some people find this utterly fascinating, and other people just think it looks like red, blue, and white on a square. But the interesting thing happens when you don't experiment with it. And you see, well, is my prediction correct? So I did this before we did the experiment. And the question was, are we going to see the same thing in the experiment? And this is a theme which runs through my career. I've always been interested in twinning, digital twinning, long before it was ever called such a thing. And so it's almost pointless if you've got any sort of physical system to try and simulate it. Think about the weather. Yeah, the weather forecast is always wrong, always. And the reason is because the equations that are being solved don't match the way that reality behaves. And so you get this divergence of trajectories. And what I've always tried to do is do everything possible to draw those trajectories together so that your predictions improve and you have a much better model of reality. And this is an example of how you can sort of hand wave and say, well, they look kind of similar, it did something and it looks plausible, but really there's nothing to tie these two things together. And so that's been a theme of my more recent work to do it. So after I finished in France, by the way, that was a postdoc, so that's typically what you do after a PhD. It's usually a stepping stone to getting a job. And back, 50, 60 years ago, it wasn't necessary to do that in order to get a job in academia. Nowadays, it's a thank you for doing this, by the way, because otherwise these would be very blanched out images. So a postdoc is a slightly unnecessary step. It's necessary if you want a job in academia, but it's been shoved in there to make it a bit harder rather than it actually having a great deal of value. You're better trained when you take a job in academia, but it becomes a bit of a meat market. And it's actually quite difficult. It's probably the worst part of anybody's. I don't know if you agree. Yeah.
I totally agree.
Yeah.
Because you keep working like PhD student at the same time as supposed to do everything else a PhD student doesn't.
Yeah.
You do need to worry about your funding more than the PhD students.
And the other thing is that one of the big responsibilities of being a PhD supervisor is that you have a duty to protect your students from the ill winds of academia. And when you're a postdoc, you're nobody's baby anymore. And so suddenly you're out fighting in those choppy waters yourself, without the protection of somebody looking after you. And that's a very difficult time. And I didn't have a particularly good time out in France. If I
So I do in France, I didn't enjoy it that much.
No, well, I sometimes I wonder how much is that. Oh gosh, this is being recorded, isn't it? Uh, whose idea was that? Whose idea was that? But yes, postdoc is a rough time, and it tests your resilience to the limit. But if you can get through that, then actually academic life as a faculty member is, in the end, a lot more attractive than your postdoc period. So then I came to Bristol, and well, this is completely different. The styles changed, the fonts changed, the whole temperament of this is completely different, isn't it? Well, this is probably oh, this has been recorded. I can't see anything here. This is probably one of the least significant pieces of academic work I've ever produced. I really can't make any jokes here, can I? I'll let you guess who's my co-author on this piece of work. It's somebody you will definitely have heard of in the faculty. Anybody else?
No, does, yeah.
No one does. Yeah, I know.
Which project did you do?
It wouldn't matter. Yeah, go on.
All right, thank you.
Yeah, looks after us all. But this was a piece of work in composites. So I was really just a hired hand to look at heat transfer because nobody was able to solve equations for that. We turned it into a reasonable piece of work. This though is much more my flavor of work. So hopefully this video will play. Oh, no, it clearly doesn't. What's wrong? Graphics? Give this a go. Vectors. So I'm not sure what's causing that to. Using that not to play. Okay, so I'll roll it manually. So this is basically an overturning tank again, and you see the same sort of thing. But this we did in the lab across the road in the Queen's building. So this is an experiment that we did. The purpose of which was not to do an experiment, but was really to get this idea. Get this idea of digital twinning going. And so here we have the corresponding simulation to that. We worked incredibly hard to ensure that that and the processed image that came out of the experiment that you just saw the video of, to make sure that those are as similar as they can possibly be, both qualitatively and quantitatively. It took us about 6 months, possibly more than that, to try and get those to be as similar as we can. But it's still the same problem. There's still the two trajectories. You solve equations that are basically wrong, and it's a varying degrees of accuracy, and you've got an experiment that goes off in a different direction. And so you have problems there philosophically about what you're doing and why, and it's something I've only recently resolved. I've spent 15 years trying to do this, and it's only recently that we've got a handle on how to actually tackle this problem. So here's another thread of work. I've been here a long time, I realized when I was putting this together the other night. I've been here for 10 years. And in that time, you did quite a lot of work, it turns out. Doesn't feel like that at the time, but this is a completely different thread of work, looking at waves. And so here, we use a different technique. This is an experiment. And we have essentially just a bunch of pistons that move up and down, and they move something we dub a magic carpet. That magic carpet moves up and down and produces some waves. And these are waves that occur in the ocean. They're very important for transporting tidal flows around and energy around. So there's a sort of natural science aspect to some of my work. And we managed to find something. This doesn't look any different to the last one, really, except because something that we didn't quite understand was happening there, we discovered something new that nobody had ever noticed before. So this is a breaking wave. You see it at the beach all the time. So you think, what did we do? What's this about? Well, nobody's ever made a wave break at far from the beach before. No waves have ever broken far from the beach. But in this case, we managed it, and we managed that by firing two waves at each other, two wave beams. These waves traveling beams, they sort of travel that direction, with another one traveling like that, and the combination of those is causing stuff to happen. Don't completely understand it, but because nobody had ever done that before, we were able to publish that in quite a reputable journal. What I was more interested in, again, is this idea of twinning things together. And because waves are a bit simpler than turbulence, because of something you may be familiar with, something called non-linearity, waves are a bit more linear, and so they're a bit easier to handle. And so you're able to get better predictions. And so this is the same idea. We want to do this digital twinning thing. We want to get our experiment to match our simulation. And so different simulation method all together, but it enables you to get a pretty good estimate of the flow. You have to take a lot into account. You have to work quite hard, but once you do it, you can get things to look the way they should. And if those words mean anything to you, they probably don't. But there's a lot of machinery in here. You know, this is like 30 pages of algebra and mathematics to get to the point where you can make these predictions reliably. So this is a long and ongoing project. Been going since 2009. So there you go, 15 years I've been working on this sort of thing, and we're not finished yet. You know, this is a long haul. And that's the reality of a lot of projects in my field. You know, it's a relatively slow moving field. It's very difficult to make any progress at all. But when you do get something to work, it's big news because it's so difficult. I'm using another buzzword here, big data. You might have heard it. It's very out of fashion this week. Next week, who knows? Big data. Data science, it's now called, for those in the know. No? What's the new one?
Just that they keep changing names, that they mean the same thing. It used to be programming, then software developer, then software engineering.
I know.
His Majesty must have before. Data science.
Exactly. I know. So never assume because something is a new name that it's clever. That's a universal piece of advice. It's usually just a clever marketing trick. So I always acknowledge fully when I use these buzzwords like digital twinning. I've been trying to do it for 15 years, long before there was any recognition that it was a thing. What's big data? Well, it's statistics. the interesting thing is that people hadn't thought that it was useful to use statistics to do lots of problems. So they applied it to lots of problems that they hadn't looked at previously. And fluids was one of them. And so we were one of the first people to actually develop and to use big data techniques in fluid mechanics. And what you see here is effectively, in order to explain what's going on, the maths is complicated, but basically you have a linear guess. That makes any sense. So you make a linear estimate of what you think is going to happen. But using that, you then have additional effects you can account for if you take the next term in the series. And if you take the next term in the series, you get second order effects. And then that's a correction to what you had before. And then you can go one term further in the series. And if you do that, then you get the third order terms. And as you increase in complexity, you start to recover the behavior of the actual thing. So what you saw on the previous slide, this one here, is the same as what you want to see here in the top right hand corner. That's the same plot in the top right hand corner. And so our simulations are basically laid out sequence by sequence, taking more and more terms into account, and then lots of different nodes, different frequencies going on. But these are temporal frequencies that have a spatial characteristic. Somebody somewhere will teach you about eigenmodes if you haven't come across it already. But that's effectively quite the same. That's what these are. And the interesting thing is that once you get to third order, you can do a direct comparison using these new fancy big data techniques in fluids. You can decompose that image at the top, not just the image, but the whole video sequence, and then decompose it and then map across and check that you've got things right. And so you can see here, for example, we're pretty close. Our estimate from the prediction is pretty close to what actually happens. And when you get that sort of match in an experiment, you raise the flag. So this was published in the premier journal for fluid mechanics, because it's just so difficult to get stuff to match. You know, to make the real world look like your idealized mathematical model is a triumph, and that's really the goal of this kind of research, is to do that kind of matching. So if you can do that, then you've got confidence in your model, and then you don't need to do any more experiments. You can go back to your model and play around on your computer all day long, much cheaper and much quicker, and then you can generalize and you can do everything else with that model. And so suddenly you've validated your model in a way that you can trust. So that's the trick there. But the techniques, have you done any statistics? Am I going to just go right across the top of your head? If you've done a little bit, you've done probability, conditional probability, Bayes theorem.
Yeah.
What about principal components analysis? No. Yeah, okay. So what this uses is basically a way of finding average directions and clusters of data. Okay, so you've got a smudge of points and it draws a line, a best fit line through it. Have you ever made a best fit line? Yeah. This is just a multi-dimensional best fit line. That's the way to think about it. And if you can persuade me that anybody's doing anything else than this is basically all everything boils down to, it seems, is finding lines of best fit and assuming Gaussian statistics and things. So that's what we did there in a nutshell. A lot more to it than that, but not for today. Why this has got stuck. There we go. What else did I do? A whole pile of other stuff. Don't do this at home. But I find it intriguing how little we know about anything. So I set off a PhD student looking at raindrops. Turns out nobody knows how they form. Certainly the Met Office doesn't know how they form because they get the forecast wrong every other week. But Maybe the reason for it is because they don't actually know how it works. And this is something that's only recently dawned on me. Most things that we take for granted, people don't know how they work. Another one, I've got another PhD student at the moment working on evaporation because nobody knows how that works. And you think, oh, well, I don't know anything about that, but somebody must, is what you think. If you assume that every other field that you don't know about must be this great body of knowledge that everybody understands, it's not like that at all. Nobody knows anything, including me, but nobody knows anything. And so if you want to ask a question, then you have to go away and do the hard work yourself. So what this project is about is basically looking at how particles move in flow. Then raindrops are just particles. A good approximation, and they don't quite follow the flow. So the wind blows, you would expect particles to move with it. That's not true. They almost follow the flow, but they have weird effects due to where they had previously been. And if you must have done the Laplace transforms, might do the Laplace transforms one day, or is that too old? Is that too old school for electronics? Electrical. Do any control theory? Yeah, dear. Well, anyway, basically, the difference between the top picture and the bottom picture is what happens when you take account of the effect of a Laplace transform. And you get completely different behavior. If you take it into account, you get more rain, basically. As you can see, you get these denser clusters of raindrops. So that's the bottom line on that. I'm struggling here to get this to move on a slide. Let's see. There we go. This you might be interested in. This might be a bit more fun. So once upon a time,